Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titration. So let's get moving. Bam! So today we are talking about the dissociation constants for acids, bases, and water. So let's figure this out. We're going to write the products of the following reaction knowing how conjugate pairs work. I.e., conjugate pairs is a difference of a single hydrogen ion from the reactant side or product side. So this is acetic acid, that is CH3COOH. That's a vinegar, acetic acid. In solution, therefore, plus water. So I need to write the conjugate pair for acetic acid. So acetic acid has an extra hydrogen ion added on to this from the acetate ion. So that hydrogen on the right-hand side of acetic acid. So I need to remove that hydrogen ion, and then I will have the acetate ion as a conjugate pair on the product side. Where is that hydrogen going to go? That hydrogen is going to now attach to the water molecule, which is the reactant side of H2O that you see as HOH. Okay, and you're going to now have H3O1+. Okay, so that's how I'm going to write the conjugate pairs, is I'm going to change the number of hydrogen ions by one of both reactants. That is, one is going to remove a hydrogen ion, one is going to gain a hydrogen ion, such that I have conjugate pairs. So here are the conjugate pairs, and I'll point these conjugate pairs out to you. These two are conjugate pairs. The one on the reactant side is acetic acid, the one on the product side is the acetate ion. The one that has more hydrogens by one is the conjugate acid. The one that has more or fewer hydrogen ions is the conjugate base of the two. Then here's the other conjugate pairs. I've got water, HOH, and H3O1+, the hydronium ion. Okay, and the conjugate base has one fewer hydrogens than the conjugate acid. You should see that this follows that conjugate acid-base pattern, of which is you have an acid and a base on the reactant side, and you have an acid and a base on the product side. You will never have an acid and an acid, or a base and a base. Okay, so you got conjugate acid-base pairs. That's how you're able to write the products. Okay, remember the equilibrium constant expression of KEQ and their values and what we talked about before? How did we arrive at the KEQ values? Well, it was products divided by the reactants with the stoichiometric coefficients as exponents, except for solids and liquids, which are not included. That's what we talked about before when we talked about KEQ expression. So we're going to be doing the same thing here with that equation. Okay, we're going to write the equilibrium constant expression for that above reaction. Okay, now I want to point out something here. There is water. That's HOH, which is H2O, and that is a liquid. Are liquids or solids included in K expressions? That answer is an absolute resounding no. So that means that this HOH is not going to be included in the K expression. So my K expression is products over reactants with the stoichiometric coefficients as exponents. The coefficients on this problem are ones, so that's not a problem. So you should see that water is not included. And this is not just a KEQ this time, this is a Ka, which means that this is an acid. That means that there is, look at this, say, look at the KEQ, Ka expression, and then look at that equation, and I'm going to point out something for you, and that is the hydronium ion. That hydronium ion corresponds to a Ka value. That hydronium ion lets you know that this is an acid, because acids produce hydronium ions. Okay? All right. This Ka value, you can find, it's a tabled value in the appendix of your textbook of Ka values or within your chapter. And it's 1.8 times 10 to the negative 5. That times 10 to the negative 5 should let you know that this is a reactant-favored reaction. I want you to look at the two equilibrium arrows that I had originally drawn out for this problem here. And you should see that the longer arrow is going towards the reactant side. That is letting you know that this reaction is reactant favored, and the K value for this, the Ka specifically, is less than 1. Okay, so the Ka is related to the strength of the acid. The smaller the Ka, the weaker the acid. Since this Ka is less than 1, it is reactant favored and it is a weak acid. Notice that all the strong acids that we delineated before had Ka values that were greater than 1. They had positive exponents, and that's why they were strong, because they dissociated 100%, whereas acetic acid here, or vinegar, will dissociate less than 100%. That's why the equilibrium lies far to the reactant side to the left. Okay, hopefully that makes sense for you. Okay, oh, so here's a little question for you. Are crows acids or bases? Good question. So, crows are acids because they're always screaming acid dissociation constants, that is Ka's, all the time. Thank you, Mr. Grubb. All right, dissociation constants for acid bases and waters. We're continuing here. We're going to write the products for the following reaction, knowing how conjugate pairs work. That is a difference of a single hydrogen ion of the reactants to the product side. Okay, so there we have ammonia. That is NH3, which is ammonia. Okay, that's going to be aqueous ammonia. The other reactant is going to be water. I wrote it as HOH so that you can see what's happening here. Now, there's an addition or a subtraction of a hydrogen by coming up with the products from the reactant. So I'm going to add a hydrogen. I'm going to subtract a hydrogen such that I get conjugate pairs. Okay, and here are the conjugate pairs that I get. I'm going to show you what the conjugate pairs are. I've highlighted these in blue. This is ammonia on the left, ammonium ion on the right. Ammonia is a base. Ammonium ion is an acid of the conjugate pairs because ammonia has one fewer hydrogen. That's why it's a base. Ammonium ion has one greater hydrogen, and therefore it's an acid of the two. The other two conjugate pairs is the water and the hydroxide. Okay, the water has one more hydrogen, the hydroxide has one fewer hydrogens. Therefore, the hydroxide, which has fewer hydrogens, is the conjugate base of the conjugate pair of the acid, which is the water. Okay, again, you should notice that water is amphoteric. It can behave as both an acid or a base. If you look at this slide right here and the previous slide with the acetic acid. Okay, remember equilibrium constant expressions, those are KEQ values, that is products divided by reactants with the stoichiometric coefficients as exponents, but what are not included, that is the exception of solids and liquids, which are not included. We're going to write the equilibrium constant expression for that above reaction. I'm going to point out that we do have liquid water here in this, and therefore that water is not going to be included. So we're going to write the K expression, that's products over reactants, stoichiometric coefficients as exponents, and bam, that's right there. Okay, you should know that, look at that K. I didn't write KEQ this time, and I certainly didn't write KA either. I wrote it's a KB because this is a base. Bases produce hydroxide ions. So I want you to highlight on the KB equation there and on the reaction up above, I'm highlighting the hydroxide. So you should see that KBs have hydroxide in them, KAs have hydronium ions in them. This is a table value just like it was for the Ka values. There's a table in the back of your textbook in the appendix or within the chapter that has KB values just like they have Ka values. And this is 1.8 times 10 to the negative 5. This Ka is less than 1, therefore it's reactant favored. Okay, this Kb is related to the strength of the base. The smaller the Kb, the weaker the base. Since this Kb is less than 1, it is reactant favored and is a weak base. Okay, because it's a weak base, it's not one of those strong bases like the group 1 or group 2 hydroxides. It's a weak base. You should see that on the equation that I wrote, I had the equilibrium arrow, the longer arrow that is, pointing to the reactant side, letting you know that this is a reactant-favored reaction. Okay, all right. So we got the Ka for acids, we got the Kb for bases, and now we're going to deal with water. Okay, the ion product constant for water. So a water does something special in that it self or auto-ionizes. Okay, so here's a water molecule and another water molecule. Notice they're both liquids. Produces hydroxide ions and hydronium ions. Okay, and this is the reaction here. Okay, those lone pairs of electrons are going to attack that hydrogen, and then those that bond is going to shift into the oxygen, and now you have on the product side hydroxide and hydronium ions, respectively. Okay, we're going to write the ion product constant for water, and this is specific for at 25 degrees Celsius. In fact, I didn't mention this before, but the Ka and the Kb values, if you look those up on a table, they are at 25 degrees Celsius or 298 Kelvin, one or the other. Remember, Ks, that is equilibrium constant expressions, and any K, whether it's a Ka, a Kb, or in this case a Kw, okay, they are temperature dependent. That's very important. So when we are doing these problems here, we are assuming at 25 degrees Celsius. So products over reactants with the stoichiometric coefficients as exponents, what are not included, solids and liquids. I got two liquids on the reactant side. Therefore, I'm going to cross out those two H2O molecules on the denominator. So this actually has no denominator except for a 1. We're going to rewrite this here, and we got a Kw. The W is for water, and I got hydronium ion times hydroxide ion, and this is equal to 1 times 10 to the negative 14. This is actually a very reactant-favored reaction, but I drew the arrow on the right-hand side just to help you write the products. Okay, that Kw, the W means for water, and this is at 25 degrees Celsius. Here's a little fun fact about the ionization product constant of water and water itself. Okay, at room temperature, that's RT, only about 2 out of every 10 to the 9 water molecules are auto-ionizing at a given instant. Thus, pure water consists almost entirely of molecules and therefore is a poor, if not a non-conductor of electricity, and therefore has a neutral pH, that is a pH at 7. Okay? I'm hoping you enjoyed that video here, and here is a crazy hat. Okay, this hat works well with my goatee as far as the color. Hopefully you enjoy the hat. This hat is one of the hats, is probably the hat that started the whole hat thing, all at the very beginning. I had hair days of different colors, and then I had hats. And this was the hat that started the whole thing. The Grand Poobah hat, if you know the Flintstones. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Pass on my crazy videos to everyone you know. See you next time for more cool chemistry videos. Bye for now.